Okay, so today what I want to talk about, I want to ask a question first before I go through this, is how many of you have taken a course in numerical methods where you've learned how to solve differential equations numerically? Any of you? Nobody? You have. What did you learn? And what did you learn in that class?
I learned about the Euler's method.
Okay, so you've done some of this, but none of you have done this. Okay, all right. So what we're going to do is we're going to take this lecture because I think it's really important that we just, that all of you at least have some kind of background in this. I'm not going to. I obviously cannot give you a whole course on stability and accuracy of all these methods, but I'm going to give you just a brief overview of this. And so where we're going to start is we're going to start with, so this is just an overview of numerical methods for solving ordinary differential equations. Now, so we're going to start with problems of this form. We've got x dot equals f of t and x with an initial condition x at t0 equals x0. Now, the thing to keep in mind is that the methods for solving this are the standard ones are the ones that you would think you would conceive when you're actually trying to do this on a computer. What they're called time marching methods. Okay, so typically an ODE is solved using what's called time marching. Or just marching. We can just say marching. And marching is exactly what you think it is. It's taking a step, taking another step, taking another step. But the question is, how do you take that step? All right? So we're going to start with the main thing that gets done here is that the ODE is discretized at a sequence of points and these points are, we start with t0, t1, t2, ... So essentially what you're doing is you've got, I don't know what's wrong with the board. I'm drawing very well. You start at t0 and you take a step to t1. So there's your initial condition, x0. You take a step, and you somehow get yourself to a value, x of t1, then you get yourself to a value, x at t2, and you keep doing this, t3, and then t4, etc., and you keep going. Now, the question is that these things don't have to be equally spaced, all right? There's nothing that says that these points have to be equally spaced, all right? That's a simple way of doing things, that they are equally spaced, but there's no requirement that they be equally spaced. So what we do is we say that between any 2 points, we call the step, sometimes people refer to it as delta t. So this would be delta t. You could either say delta t0, delta t1, delta t2, actually we'll start with delta t1 because it's the first step, second step, third step, and the fourth step, and then so on. Normally what we do is we abbreviate these by just h1, h2, h3, h4. Now, the step takes us to the next point. Well, we don't have to necessarily take that as one stage. We can do it in one stage or we can do it in multiple stages. So the first thing I'm going to talk to you about are what are called one-stage methods. And they're also typically known as Euler methods because of the way that these are done. because I guess Euler came up with this first, is the first thing you do is you say that we need to approximate x dot at some point tk, right? Now, what are the ways that we can approximate the rate of change of the state, or the rate of change of x? Well, there are a bunch of different ways, and most of them are by finite differencing. Typically, this is done using finite differencing. Or finite differences. So there are a number of ways to approximate the derivative. So let's just suppose that, let's draw this picture right here. Let's suppose I'm at tk, and I have some function, and I'm sitting here at this point, and I want to approximate the derivative at this point. And I want to also be able to take a step and go to another point, call it tk plus 1. So what are the ways that I can approximate the derivative? Because I'm going to do this, if I'm going to march, I have to go from tk to tk plus 1. And if I'm using a one-stage method, which is an Euler method, I can only use the current value and the next value in order to be able to do this. So the way this is typically done is you don't normally look backwards. You go forward, and you say, well, x dot of tk is approximately x at tk plus 1 minus x of tk all divided by delta tk, which is equal to x tk plus 1 minus x, tk plus 1, x of tk, all divided by hk. Now that's an approximation. That's a first order approximation. In this case, it would look like that. Okay? So if I did this and I plugged it into that equation over there, I've got x at tk plus 1 minus x of tk all divided by hk is equal to something. Now the question is, what's the something that goes on this side? Because over here what I'm doing is I'm approximating the derivative. Over here I'm setting that derivative approximation to something that resembles what my differential equation is going to be, or the vector field that makes this an equality, right? So the question is, what do I put on the other side? I have a lot of choices. So what can I do? Well, what's the most obvious thing to do? I'm sitting here at point tk, right? I have tk, and I have the value here, x at tk. So what would be the most obvious thing to put in on this side over here? Okay, that's good. F of tk and x of tk, which from now on we're just going to abbreviate all this. xk plus 1 minus xk all divided by hk equals f of tk and xk. All right? So this is approximately equal to this. All right? Now, well, actually it's equal to this, but this is approximately equal to that. Okay? Now that method, I can rearrange it, and I can write down that x, k plus 1, is equal to xk plus hk times f of tk and xk, right? Now look what I've done. I'm taking a step. Essentially what I've done is I've said that the derivative is going to be approximated by a secant, right? Because that's a secant approximation. And it's done in such a way that if I know everything at step k, then I can get the value at step k plus 1 simply by evaluating everything at time tk and then substituting into the right-hand side and then adding a multiple of this right-hand side, which is the step plus to the to the value, right? So that gives me a time march forward. What's appealing about this? There should be something appealing about it. If it's not obvious. Is there anything obviously appealing about this?
No derivatives?
No. We're doing finite differencing now, so the derivatives are always going to be gone. The question is, what's appealing about this particular numerical method? It's really simple, right? I mean, all I need to do is take the values at the current point, and I just propagate them one step. I march to the next point. I know everything, right? I know the step length, or the step size, and I know all the values at the current point, so I can simply get the value at the next point. All right, now, you would think that this would be a great way to do things because it's really simple. Turns out that this method is extremely inaccurate. First of all, it's only good to first order. And it should only be good to first order because look what I did. I used one piece of information. What essentially am I doing? Let's look at what this method actually does, okay? This method, I have a point. I'm going to redraw that picture, except for I'm going to draw it a little bit differently. I'm starting here at x of t0, right, equals x0. And what I do is I go to point t1. So what did I do? I did a straight line, right? And then I do another straight line. And then I do another straight line. And then I do another straight line. And then another straight line, right? So each of these points here that I've marched myself to is obtained from a straight line extrapolation of the function of the right hand side of the vector field, right? Right hand side vector field. So I take this. If I do a straight line approximation, I get myself here, and I keep doing that over and over again. So clearly, if I make these step sizes too big, my straight line approximation is not going to be very good, right? Because I'm using a straight line approximation for the derivative, and clearly, if I make the step size too big, if the function actually was doing something like this, right, my straight line is going to be a really poor approximation if I make the step size too big. All right, now, the nice thing about this is, though, it only requires one function evaluation. Do you see that? The only function evaluation that's required is here. I know everything else. When I say function evaluation, I'm talking about evaluations of this vector field f, right? So I only need one function evaluation. This method here is what's called Euler forward. And it is the simplest method for integrating differential equations, and it's extremely poor. But people use it because, when you get into real logic, when I say logic, I mean when you have constraints on a logic board, like if you're actually going to integrate differential equations on a logic board, this is what they actually do. And the reason is because they don't have any computational power to be able to do much else. So what they do is they make the step really, really small, right? And then they integrate with a really small step. What's the problem with making the step really, really small? What if h is really, really small? Let's suppose this is reality, okay? When you get to if you had a flight processor and you're actually doing this on a flight processor where you've got a limited number of digits you can actually even hold on the computer, right? What happens if h is too small? If h is too small, you suffer from round-off error, right? Because as soon as h gets small enough, your machine can't even hold that many digits, so it just basically says h is 0. And eventually, if you make this sufficiently small, it says xk plus 1 is equal to xk, which is clearly not right? If h is too big, you suffer from truncation error because you're truncating the Taylor series approximation to first order, but clearly your function is doing something completely different, unless it turns out your function happens to be a straight line, which is very rarely the case, right? Because you're generally dealing with pretty complicated differential equations, so you're not going to get a very good approximation. Now, there's a way to rectify this to make it a little bit better. It's still a first-order method, but it has much better characteristics as far as stability goes, meaning that errors don't grow as quickly if you make one modification to this. So consider the following modification. To Euler forward, which is this. So instead of writing we take the finite difference, that remains the same. instead of approximating it using the value at step k, we approximate it using the value at step k plus 1. And then what we get is this. Now, how many function evaluations does this have? As compared to that over there. What did I just do? I just set the derivative approximation, right? I'm doing a derivative approximation. So it doesn't matter whether I'm here or there, right? This derivative approximation can be at either point. It can either be at k plus 1 or it can be at k. I'm saying now I'm going to approximate the derivative here, right? I'm at k, but now I'm approximating the derivative at that point right there, right? So what happens when I do this? How many function evaluations do I have? 1. Do I have a 1? It looks like I have 1, doesn't it? But what is it that I don't know? There's something I don't know in this equation. I don't know xk plus 1, right? Because I'm at xk. I haven't gotten xk plus 1 yet, right? So the problem with this equation is I don't know the value that I'm going to. So how the heck am I going to do this? Well, you do it the way that most people would conceive of doing it, which is that I'm sitting at xk, and I say, well, I'm going to make a guess of xk plus 1. And I'm going to propagate, and I'm going to do it by iteration. So what you get is you get this iteration that looks like this, is that xk plus 1 at the jth iterate is equal to xk, which I know, plus hk times f of tk plus 1, which I also know, xk plus 1 at the j minus first iterate, where j goes from 1 to capital J, which is the number of iterations that I'm going to take in this thing. Right? So what I do is I make a guess. Actually, j goes from, it goes from 1, because I started at 1. Okay? So if you look at this, you say, well, how do I make a guess of this? Well, what do I need this to do? Well, what I need it to do is, if I make a guess here, let's suppose j is equal to 1, so I got xk plus 1 of 0, right? Which is, suppose I just guess that xk plus 1 is equal to xk. A logical guess, right? I have nothing better to guess, right? I know the value at xk, so I plug this in here. Clearly, when I plug this in and put it over and solve for it, right, the value that I get out over here is going to be different from the value that I put in, right? So then I plug that value in and I stick it back in here and I evaluate it again and I get the next value out. And until the two values, the one that I put in and the one that I get out, match to within some tolerance, I don't stop this iteration. I keep going until I'm done, right? Now, usually you don't do this for too many iterations. You do it for like 2, 3, 4 iterations, and then you stop because eventually you get close enough that it doesn't really matter. Now, the thing with this is it doesn't require one function evaluation anymore. It requires at least 2 function evaluations, right? It may require more, but it requires 2 because I'm not guaranteed that the first time I plug something in and then that the output's going to match the input. In fact, in general, it won't match the input, right? So as a result, I'm going to have to do it one more time, which means I have to do another function evaluation in order to be able to get this to work. So this requires at least 2 function evaluations. At least 2 evaluations of f. This method here is what's called Euler backward. Now, what this leads to is, it leads to this whole family of methods, which are called the Euler family of finite difference approximations to that differential equation, which is that the Euler family looks like this. You've got xk plus 1 minus xk, all divided by hk, is equal to, well, at one extreme, Euler forward, I just use the value of f at the current point. Euler backward, I use the value of f at the next point, right? So what we normally have is we have something that looks like this. We have theta times fk, I'm just going to abbreviate it, plus 1 minus theta times f k plus 1. Now, it turns out that if theta is equal to 0, what do you get? You get Euler backward. If theta is equal to 1, you get Euler forward. But you don't have to set theta to any one of these. Turns out that if you set theta equal 1/2, you get what's called Crank-Nicolson. I don't know why it's called Crank-Nicolson. I think these are two guys who came up with it. But Crank-Nicolson is these two are set equal to each other. In either case, this method is the only one that's what's called fully explicit. This is what's called fully explicit. When we say explicit, what we mean is that the value of the solution at the next point does not depend upon the value of the solution at the next point. You can get it fully explicitly from the information at the previous point, right? If it's not, it's implicit. So these other ones are implicit. So otherwise, any value of theta not equal to 1 is what's called implicit. Now, without going into a long discussion about this, because this gets very difficult to actually, you can get into proofs of all this stuff. The reason that you would want to use an implicit scheme over an explicit scheme is two things. You get the same accuracy in both cases when you're using Euler. It doesn't matter whether you're using Euler forward or Euler backward. You're going to get first order accuracy. But the thing that you're going to get is you're going to get much greater stability with an implicit scheme than you will with an explicit scheme. The stability comes into the fact that if you think about picking a step size, for a given step size, the question is, does the truncation error at any point increase or decrease as you actually, for that step size, as you actually propagate forward? If your errors keep increasing as you go forward, your scheme is unstable, right? Because it's saying that no matter what I do, my error is just going to keep getting worse and worse and worse. You can't have your error grow unboundedly in a differential equation scheme, because then what it's doing is diverging from the true solution. You want your error to be limited in such a way that over a course of a number of steps, whatever error you accumulate, it's going to be bounded by some amount, and you can guarantee that it's going to be bounded. That's where the stability comes in. So you don't get stability, or as good stability, if you do Euler forward as if you do Euler backward. Euler backward is a significantly more stable scheme. All right, now, clearly, if you're doing these kinds of methods, you can see that these are very easy to implement. These are not the ones that are typically used in solving differential equations because they don't have very good accuracy. So the next thing that people do, I'm not going to do multi-step methods because multi-step methods aren't really used anymore. People used to use Adams-Moulton, Adams-Bashforth methods, but they're very complicated to code and they don't really buy you a whole lot. So what we do is we talk about multiple stage methods. These are multiple stage methods. And these are also called Runge-Kutta methods. The idea behind a multiple stage method, and there are so many of them that you can derive these as you wish, but the idea of a multiple stage method is this, is that if you're sitting at time tk and you want to go to time tk plus 1, what you do is you take the value of the function and you partition this interval into a bunch of stages. I've just done 2. Let's do 3 stages. And then what you do is you construct a set of coefficients that give you the approximations of derivatives at these midpoints, given information at the endpoints, and then you construct a linear combination of those derivatives in such a way that you place weights on them, such that the weights give you sort of an average of what the slope is over those points. A good example of this is what's called a classical Runge-Kutta method, which is the one that people typically use because it's really nice, which is that it is actually called the classic Runge-Kutta method, and it looks like this, is that and there are Runge-Kutta methods of any order that you can do this with. But what it looks like is this, is you start off with the first, you have 4 coefficients. You've got k1 is equal to h xk times fk. It's actually the value of the slope multiplied by the step size at the first point. Then what you do is you take k2 to equal, now what you do is you again take hk, and you take you take the value of x at xk, sorry, I'm doing t first, tk, and you say plus, well, I'll write it this way, tk plus tk plus 1 over 2, which is the midpoint between here and there. It's the midpoint. And then you add to xk the value of k1 over 2. So what this does is, this gives you an approximation to the slope at the first stage. That's the first stage. And then what you do is you construct the next stage, which is hk times f of tk plus 1 over 2. And then you add xk plus k2 over 2. And then k4 is equal to hk times f of tk plus 1, and then xk plus 1, xk plus k3. And then what you do is you construct an average of these slopes, and you get the following result. You get xk plus 1 is equal to xk plus 1/6 k1 plus 2k2 plus 2k3 plus k4. So you can see what happens is that basically you're weighting these different coefficients by a certain amount in such a way that the sum of the weights, and then you normalize the sum of the weights so that they wind up normalizing to 1. So it doesn't matter what the stage is. You're always going to wind up getting the summation in here of whatever the sum of these coefficients is has got to be the same as the denominator of the averaging factor in front. So basically what this does is, now you'll notice it's not a multiple step method. It's not like Euler forward, because you look and see what you need in order to be able to do this. I need the value of the function at the point k first, right? Now, to get the next coefficient, what do I need? I don't need the value of the function at the next point. I need the value of the function at the current point plus the value that I got from the first stage, right? So I'm not actually evaluating the function at a point that I don't know the value at. I know xk, and I also know k1, right, because I just computed it. So this is staging, because in order to get the next stage, I have to compute the value from the previous stage. I can't do this. I can't do this one before I do this one. I have to do this one first, then I do this one, and then I do this one, and then I average them out. And you can see that when doing this method right here has fourth order accuracy. It's also called the classical fourth order Runge-Kutta. It's got fourth order accuracy, which means the truncation error of this is good to order h to the fourth. Right now, the problem with this method, or if you say there is a problem, is you need a lot more function evaluations in order to be able to do it. So it's a more expensive method, right? But it also gives you a lot more accuracy in the scheme. It also has very good stability properties as if you go through. And this is why I highly recommend for any one of you, like, it's just not possible for me to delve into this in lots and lots of depth here. But if you really want to learn about differential equations and numerical solutions to differential equations, I highly recommend taking a course on numerical methods. There's one class, and I kid you not, well, maybe two classes, when I was a graduate student that were completely indispensable to me. One was when I was my first year of grad school at Michigan. I took this course on numerical solution of partial differential equations. That was just one of the roughest classes I've ever taken in my life, because we based this. Now imagine, okay, this is the year is 1988, okay? So 1988 was not like 2012, all right? 1988 was a very different time period. We didn't have MATLAB all over campus. We didn't have laptops that we could go to. We didn't have our MacBook Pros and our other Apple machines and all these other PCs and everything that you guys have now. What we had was, we had these clusters of computers around the University of Michigan campus where you could log in with your login ID and you could access the software. And the software that we had back then was, we had Fortran compilers. We had Fortran compilers. And C compilers. Right? We had C compilers. We had C compilers. And C++ was just kind of just getting started at that point. So really didn't even have C++ compilers. Fortran compilers and C compilers. So you had to write all your code in Fortran. So there I was, first year as a graduate student, I'd never done this before. I'd never programmed I did a little bit of programming in Fortran when I was in college, but really we learned Pascal when I was taking computer science at Cornell, and so even my programming was completely obsolete. So I went to my professor, and he was a real hotshot. He is a real hotshot. He's a really famous guy in computational fluid dynamics now. He was a really young guy back then. He'd just gotten his PhD from MIT, and of course, anyone who gets their PhD from MIT is by definition like, the world's greatest person. So he thought of himself that way. So I went to his office and I said, I need some help. And he said, what do you need help with? I said, I don't know how to program in Fortran, and I don't know how I'm going to do in this class. He said, well, I can't really help you with how you're going to do in this class, but here's a book on Fortran. Figure it out. So what did I do? I trudged my way down to the computer cluster, with my backpack and everything, and I'm sitting there trying to learn how to program in Fortran as I'm actually taking this class. And man, did I struggle. I struggled, all right? This was like real programming, right? I had no idea what I was getting myself into. Teaching myself all the stupid things, like, hello world and all this stuff. It's like, can you imagine learning this on the fly as you're actually trying to learn numerical methods for solving partial differential equations. It was the hardest class I ever took in my life. Absolutely the hardest class I ever took. And it was absolutely the best class I ever took because I learned so much in the process of doing this. I learned so much theory. I learned so much about how you actually solve things on a computer. Nothing ever replaces a good numerical methods class. It doesn't. I worked really, really hard. And I remember I got an A- in that class, and I was so happy I got an A-, right? Well, actually, I wasn't that happy. I was happy I was happy 6 months later when I realized how everybody else did, because everybody else did really badly. So I was really thrilled that I got an A-. And I asked him why I got an A- and I didn't get an A, and he said to me, you were number 6 in the class, and I only give A's to the top 5. And I said, well, that's ridiculous. I said, well, he said, you did really well in the class. You got an A-. And I said, yeah, but I wanted an A. He said, well, that's my rule. I only give A's to the top 5 students in the class. So that was his rule, right? I guess everyone has to have a rule by which they grade. But anyway, the moral of the story is not the A-. The moral of the story is that taking a good course in numerical methods really helps. I took another course in numerical methods when I was at Princeton a few years later. And again, it was just an absolute, just a crazy class. It's like we would my professor there was a little bit of a maniac. He would write the notes for the class on the board. He would say, "Oh, I come in about 5-10 minutes early," and I would jot a little outline of what we were going to cover. And his 5 or 10 minutes became 15 minutes, and then became 20 minutes, and then became a half an hour, and then became 45 minutes. And eventually, he would spend an hour before class plastering 7 blackboards full of all the notes for the class. So everybody would show up for the class an hour early to take down all the notes, and then he'd start teaching class. And he said, I don't want you to copy anything down from the board, because then I just want you to listen to me. But everyone wanted to write down everything from the board, because he wouldn't hand out copies of his notes. So we all sat there. So essentially this 50-minute class became 2 50-minute class periods, because we'd spend the first 50 minutes copying down what he wrote down, and the second 50 minutes listening to him. Really great class, though. He was a fantastic professor. And the thing you learn when you take these classes is you learn the connection between these discrete approximations and the continuous problems that you're trying to solve. Because one of the things you don't ever want to do is you don't ever want to go into this completely naively. Because if you go into it completely naively, you don't know whether what you're getting even makes any sense on a computer. I mean, you no longer have. Look at this. Let's look at this problem in a slightly different way. This is something that always kind of made me realize that you're doing something very different when you discretize as compared to when you're solving the continuous problem. So if you look at the continuous problem, you've got x dot equals f of t and x. So what's the unknown parameter in this problem? Or what is the thing you're solving for? You're solving for x, right? But if I discretize, as soon as I discretize, look what happens. I've got xk plus 1, I'm going to write it down this way, is a function of what? It's a function of tk, it's a function of xk, it may be a function of xk plus 1, and it's a function of this parameter h sub k. See, what did I do in the process of doing this? This problem actually has an additional parameter in it. That problem doesn't have the parameter h in it, right? So what I've done is I've actually made this structure richer by doing this. When I say richer, I don't mean more money. I mean the fact that this problem may have a solution that this problem doesn't have, right? In fact, it will, right? For every value of h, there's a solution to this problem, right? So it's a whole family of solutions, which means that if I change h, I change the solution, right? This problem has, assuming that there are appropriate Lipschitz conditions and continuity conditions on this function f, this problem only has one solution, right? This problem doesn't. This problem actually has an infinite number of solutions, and it's infinite based on the value of the parameter h, right? Every value of h admits a different solution. So it's much harder to solve this problem and be confident that you've actually gotten a good approximation to this problem because you've introduced this parameter h. So it's not just I introduced the parameter h. That's the naive way of looking at differential equations, is that you say, well, I'm just introducing this parameter. You're not just doing that. You're actually, in the process of doing this, you're changing the problem. You're not solving the same problem. You are saying, I need to solve this problem. That's not solving this problem. Okay? So when people solve differential equations on a computer, the one thing you should never say this, all right? I have a solution to the differential equation. You should never say that. You say, I have a solution to an approximation of the differential equation, and it's based on this particular approximation that I made. It's not a solution to the differential equation. If it were, then you wouldn't be doing it numerically. You'd be doing it analytically, right? So it's not a solution to your differential equation. It's an approximation to the differential equation, and you're solving the approximation. You're not solving the original problem. Now, the one thing that I want to talk about before we finish today, because we're headed down this direction, which is that this is it's not a sleight of hand. It's a way of rewriting this. But let's take Euler forward for a second, and let's suppose that I string these equations out sequentially. So what I'm going to do is this. So we write Euler forward sequentially. And what I mean by sequentially is this. Is that x1 is equal to x0 plus h1 times f0, right? x2 is equal to x1 plus h2 times f1. And I can keep doing that. xk plus 1 is equal to xk plus hk times fk. Make sure I do this right. K plus 1. No. Sorry, this should be a 0. 1. hk fk. Right? So if you look at these equations, you could say, well, the way I introduced it originally was, I said that if you know the value at t0, of x0 at t0, you can solve for x1. And then you can plug that in and get the value for x2. And then plug that in and get the value for x3 and keep doing it. Or what I can do is I could solve all of these simultaneously. So I can rewrite this system like this. I can write it as x1 minus x0 minus h0 f0 is equal to 0. x2 minus x1 minus h1 times f1 is equal to 0. And I can keep doing this. xk plus 1 minus xk minus hk times fk is equal to 0. Now, you say, well, I haven't done anything in the process of doing this, right? All I've done is I've just rearranged these equations. But there's a big difference now. Now what you do is you say, I'm going to solve these. Suppose you say, I'm going to solve this simultaneously. I'm no longer going to solve it by time marching. I'm not going to take the previous value and plug it in to get the next value. I'm going to solve all these at the same time. Can I do that? Sure, I can. What you can do is you can say y. It's a vector. It's going to equal x0, x1, all the way up to xk plus 1. Right? And you could say that you can, since you're only doing this, I can call it y tilde if you want to, is equal to x0 up to xk. So what you can see here when you write this is you get a system. I may not need that y tilde. So, hang on a second. So when you write this system out, you can see that I could construct a function g, which is a function of y. It's a function of y tilde, and it's a function of all the h's. Let's call the whole vector of h's h equals 0. I can do that, right? Now, if I solve that, I could solve for all these at the same time. So if I want to, I can drop the dependence on y tilde because it's really just a function of y because I don't need it. Where h is equal to all of these values, h0 up to h sub k. Now, if you look at that, you see that that's a system of algebraic equations, right? So I can solve that with a root finding technique, right? And if I solve for it using a root finding technique, I get all the values of x simultaneously, right? So what I can do is I can turn this problem from this sequential time marching process into a single root finding problem where I just say I'm going to solve for the roots of that system. This right here, this technique of doing this is what's called collocation. It's collocation because what you're doing is you're saying that at each step I'm going to approximate the derivative with the right-hand side of the differential, with some function of the right-hand side of the differential equation, and I'm going to do that at every single point, and I'm going to group them all together into one big system of equations, and I'm going to solve that system of equations. That system of equations is now done by collocation, and the reason that you call it collocation is because you're saying whatever the derivative approximation is, at that point in time, I'm going to set it equal to the right-hand side of the dynamics. I'm collocating. I'm putting two things in the same place. That's what it means to collocate, right? I have one thing which is a derivative approximation, another thing which is the right-hand side vector field. I'm saying these two things are going in the same spot. They're being set equal to each other. That's why it's called collocation. You can see that all I've done in doing this is I've rewritten it by the scale factor of h. I could always write it as x1 minus x0 divided by h0 minus f0 equals 0. It's the same thing. So if you actually look at it in its original form, what it would look like is this, without doing the rearrangement the way I did it before. It's the same thing, but I'll write it in. You say x1 minus x0 over h0 is minus f0 is equal to 0, and you keep doing that. xk plus 1 minus xk, all divided by hk minus fk is equal to 0. So what you're doing is you're saying that this system of algebraic equations now has to be satisfied. And you can see that the system of algebraic equations says that the difference between my derivative approximation and my vector field has to be 0. It's basically saying put those two things in the same spot, make them equal to each other. Whatever values of x satisfy that system of equations, that's the solution. I don't have to do it sequentially. And in fact, now when you do this with Euler backward, let's suppose I did this now with Euler backward, and then I'll stop. And then we can talk about this more on Wednesday, because this is just kind of a lead-in to all this stuff with collocation. Which is that with Euler backward, the nice thing about this is, remember what happened before with Euler backward was we didn't know the value at xk plus 1, right? We want to get there, but in order to solve the problem, we had to iterate, right? But if you write this system of equations out, you can solve this problem this way. Now you can see that this system of equations doesn't involve any different set of variables than that system of equations does, right? I can solve this system the same way I could solve that system over here. It's just that I don't have this last value over here is a function of my endpoint, but that's okay. It's a function of the endpoint anyway because it's sitting over here, right? So I could solve this for all these values the same way I could solve that system, algebraic system by root finding. I could solve this algebraic system by root finding. Now it doesn't require me to have to iterate at each step to be able to get the solution. I'm just going to plug in and I'm going to solve whatever my root finding technique is, whether it's Newton's method or some other kind of method, a secant method. I can use that method to get me a root for that system of equations, right? So this becomes easier from the standpoint of root finding because it really doesn't matter which one of these I use. I can use either one. And this is a better method than that one is, so you're better off using this one, even though it looks like it's basically the same thing, but it actually has a difference in the fact that each of these is evaluated. Right-hand side is evaluated at the end point. So we're going to stop here because that's my sort of overview of differential equations or numerical solutions to differential equations leading into this whole structure of collocation, which is what we're going to do in the next several lectures. Okay? So we'll talk about collocation, and then we'll talk about how you actually do collocation, what the different types of collocation are, and then I'm going to talk about spectral collocation, which is a lot of the stuff I do research on right now. We're going to go through all those methods, and then we're going to talk about supporting techniques. And at that point, you'll probably be in a position to be able to think about how you want to actually go about doing the project. And then what we're going to do is, then we're going to go back. So I'm going to kind of go backwards, which is I'm going to go back to some of the things that we didn't talk about earlier in the class, which are special things that come up with inequality constraints with indirect methods. But I wanted to do this first before we do that because this will allow you to be able to start thinking about what you want to do for your project, and then we can fill in some of those gaps in March. Okay. All right.